Doppler's effect. So what is it? It is the apparent change in frequency of a traveling wave, could be a sound wave or an EM wave or any other wave, as a result of the relative motion between the source that's producing the wave and an observer. So let's study in this case a sound wave. So let's have some definition. U subscript S represents the speed of the moving source. V represents the speed of the sound wave produced by the moving source, and the frequency of the sound wave produced is 1 Hertz, meaning every 1 second a sound wave completes one cycle, and therefore the wavefront would be given off at intervals of 1 second. So we are looking at circular wavefront because the sound travels in all directions, and for this scenario we are looking at when the speed of the moving source is smaller than the speed of the sound wave. So I have with me a diagram consisting of 5 crosses. Each cross represents the starting position of that moving source. So at time t equals to 0, the moving source is right at the middle of the cross, denoted by this dot, and the cross at all other time frame represents the starting position of the moving source. So at time t equals 0, the source moves to the right, and at the same time gives off the first wavefront. So at time t equals to 1 second, the wavefront would have expanded to something like that, and the moving source, being slower than the speed of the wave, would be lagging behind, and this is the position of the moving source. So this position of the moving source will be the starting position for the second wavefront. So the start point of a second wavefront. So at time t equals to 2 seconds, the first wavefront that was given off at time t equals to 0 would have expanded and at the same time the second wavefront that started off at time t equals to 1 second would have increased, and its center is here. It will have moved off from its center that is denoted by this position, and at this point the source would have traveled here, and this would be the start point of the third wave. So at time t equals to 3 seconds, the first wavefront would have expanded very much bigger, and the second wavefront, denoted by the blue circle, would also have expanded much bigger, and the third wavefront, denoted by the green circle, would have expanded by this. And where is that moving source? It would be somewhere here. So looking at the time t equals to 4 seconds, the first wavefront would have increased in size as shown here, and the second wavefront would be here, and the third wavefront would have increased to this size, as shown here, and the fourth wavefront would have increased to this size. And the starting point of the fourth wavefront is over here. And at this point, t equals to 4 seconds, where is that moving source? It would be somewhere here. So you get the point. This would be the wavefront diagram for when the speed of the moving source is smaller than the speed of the sound wave produced. So if we now look at another scenario where the speed of the source is equal to the speed of that sound wave. So again, I have my crosses. So how would my new diagram look like? So the first, again, moving source at time t equals to 0 is here, and it starts to move to the right at time t equals to 1. As it gives off the first wave, the wavefront would look like that. And where is that moving source? It's right at the edge here, because the speed of the moving source is equal to the speed of the sound wave. And at time t equals to 2 seconds, the first wavefront would have expanded, and the second wavefront would look like that. And where is that source? It would be here, right at the edge. And for the time t equals to 3 seconds, the first wavefront would have expanded, and the second wavefront similarly would have expanded to a big circle as shown here. And the third wavefront would also have expanded. And where is that moving source? It would be here. And for time t equals to 4 seconds, the first wavefront is as shown, the second wavefront is over here, the third wavefront is over here. The fourth wavefront will be over here. And at this point, the moving source would be right here. So this is a case when the speed of the moving source is equal to the speed of the sound wave. Now let's look at another situation when the speed of the moving source exceeds the speed of the sound wave produced. So how would that look like? Let's analyze. Time t equals to 0 seconds. The source would start off from x, moving to the right. At time t equals to 1 second, the first sound wave is produced, and at this point, since the moving source is faster than the speed of the sound, the moving source will be here, and this will be the center position of the second sound wave. So at time t equals to 2 seconds, the first wavefront would be here, the second wavefront would be here. And where is that moving source? It's still ahead here. And at time t equals to 3 seconds, the first sound wave would be here. The second sound wave would have expanded here. The third sound wave would be here. And where is that moving source? It's still right in front here, faster than the speed of the sound wave produced. At time t equals to 4 seconds, the sound wave would be here, and the second wavefront would be here. The third wavefront is over here. The fourth wavefront is over here. And where is that moving source? It's right at the front here. So at this point, I would like to also mention the phenomenon known as sonic boom. Now, sonic boom refers to a loud sound that's produced. Now, where did this loud sound come from? It comes from this scenario where the speed of the moving source exceeds the speed of the sound wave. So if you look at the time t equals to 4 seconds, look at this region here and this region here. Now you would expect that there is overlapping of the wavefront, and when wavefront overlap, the amplitude of one wave is superimposed onto the amplitude of the other wave, and amplitude refers to the loudness of sound. So when one amplitude adds on to the second amplitude, the loudness is essentially multiplied. So if I have a person standing here, the sound wave comes right at the person and it hits the person head on, the person would hear a sound that is two times the loudness as if it was a single wave. So sonic boom occurs with a loud bang. So that's the reason why sonic boom is not desirable when airplanes travel at supersonic speed. That's more than the speed of sound, because it causes huge disturbance to the people living in the vicinity. So with that, I hope you understand a little bit about Doppler's effect and the wavefront produced in the 3 scenarios mentioned.